Helium is the second element on the periodic table, with the atomic number 2, and it holds a special place in the universe. As the second lightest and second most abundant element in the observable universe, helium is a colorless, odorless, tasteless, non-toxic, and inert gas under standard conditions. It belongs to the noble gas group in the periodic table, which means it is highly unreactive due to its full valence electron shell. Its atomic structure consists of 2 protons, 2 neutrons, and 2 electrons, making it incredibly stable. Helium's unique physical and chemical properties make it critical for a range of scientific, industrial, and medical applications. Helium was first detected in the Sun before it was discovered on Earth. In 1868, French astronomer Jules Janssen observed a mysterious yellow spectral line during a solar eclipse. British astronomer Norman Lockyer later identified this line as coming from a new element, which he named helium after the Greek word for the sun, helios. It wasn't until 1895 that Scottish chemist Sir William Ramsay isolated helium on Earth by treating the uranium-containing mineral cleveite with acid and capturing the gas it emitted. This marked a significant milestone in the discovery of elements and the study of noble gases. One of helium's most remarkable characteristics is its low boiling point, just 4.2 Kelvin, or minus 268.93 degrees Celsius. It is the coldest liquefiable element, and the only element that does not solidify under standard pressure, no matter how low the temperature. To freeze helium, you must apply both extremely low temperatures and high pressures. This property is crucial for many advanced technologies. For instance, liquid helium is essential in cryogenics, particularly in cooling superconducting magnets used in MRI machines and scientific research instruments like those found in particle accelerators. Because of its low atomic mass and non-reactive nature, helium also plays a key role in many industrial processes. One well-known use is in lighter-than-air applications. Helium is used to fill balloons and airships because it is significantly lighter than air, and, unlike hydrogen, it is not flammable. This safety feature makes it the preferred lifting gas despite its higher cost. In addition to lifting gases, helium is used as a protective inert atmosphere in processes such as arc welding, where its non-reactive quality prevents oxidation of metals at high temperatures. Helium is also a critical component in the field of aerospace. Because of its ability to withstand extreme conditions and its inertness, helium is used to purge fuel and oxidizer tanks in rockets, to pressurize fluid systems, and as a cooling medium for satellite instruments. Its predictable behavior and resistance to chemical reactions make it invaluable in these sensitive and highly controlled environments. Additionally, the United States space program has historically been one of the largest consumers of helium, especially during the Apollo missions. Another important area where helium proves essential is in deep-sea diving. At great depths, breathing regular air can lead to nitrogen narcosis, a dangerous condition caused by nitrogen's effect on the nervous system under pressure. To avoid this, divers use a mixture of helium and oxygen, known as heliox, which allows for deeper dives without the harmful effects of nitrogen. Helium is ideal because it doesn't dissolve into body tissues the way nitrogen does, reducing the risk of decompression sickness. In scientific research, helium's unique quantum properties make it a subject of fascination. When cooled to near absolute zero, helium-4 becomes a superfluid, a state of matter with zero viscosity that can flow without losing energy. This means that it can climb the walls of containers or pass through ultrafine pores that no other liquid can. These behaviors challenge our understanding of classical physics and make helium vital in the study of quantum mechanics and low-temperature physics. Helium-3, a rare isotope, also has potential applications in nuclear fusion and quantum computing. Despite being the second most abundant element in the universe, helium is, actually pretty rare on Earth. It's formed through the radioactive decay of heavy elements like uranium and thorium in the Earth's crust. The resulting helium atoms then accumulate in natural gas reserves, where, they can be extracted through a process called fractional distillation. However, helium is non-renewable on human timescales. Once it's released into the atmosphere, it rises all the way into space and is, lost forever. This makes helium conservation and recycling more and more important, especially as demand keeps growing in high-tech industries. In response to concerns about supply shortages, some countries, particularly the United States, have developed helium reserves. The United States Federal Helium Reserve, located in Amarillo, Texas, was established way back in the 1920s and became a strategic stockpile for both military and industrial use. However, debates around privatization, depletion, and management of this resource have sparked discussions about global helium policy. Meanwhile, scientists are exploring alternative sources, including helium trapped in certain mineral deposits or generated in nuclear reactors, but honestly, these methods are still limited in scale. From a chemical standpoint, helium is a noble gas, meaning it rarely forms compounds. This is due to its closed-shell electron configuration, which makes it highly stable and unreactive. While some exotic helium compounds have been synthesized in laboratory conditions, such as helium hydrates or ionic compounds involving helium under high pressure, they are honestly not stable under normal conditions and have limited practical use. This chemical inertness is precisely why helium is so valuable in situations where contamination or unwanted reactions must be avoided. In medical applications aside from MRI cooling, helium is also used in respiratory treatments. A helium-oxygen mixture can be used to treat patients with asthma or other obstructive airway conditions. Because helium is less dense than air, it can carry oxygen more easily through narrowed airways, making it easier for patients to breathe. This use really highlights helium's therapeutic potential and versatility in clinical settings. In summary, helium is far more than just a party balloon gas. Its unique physical and chemical properties make it essential to modern science, medicine, industry, and technology. From cooling superconductors to enabling space exploration and quantum research, helium supports some of the most advanced systems we rely on today. Its rarity on Earth and irreplaceable applications highlight the need for careful management and innovation to secure helium supplies for future generations. As we deepen our understanding of this extraordinary element, its role is only set to grow in importance.